So what is the percentage of broiler chickens sold in the United States that are infected with this Campylobacter infection, whatever, bacteria? Um, this is what we're going to do with a confidence interval. We don't know what that true population proportion is. It's something we want to know, but it'd be really hard to try to test all the broiler chickens sold in the United States. So what we're going to do is we're going to construct a confidence interval, which is essentially taking a sampling distribution as we know it and kind of turning it around. Instead of building a sampling distribution based on a known population proportion, we're going to say, all right, well, that's what we're looking for, that population proportion. How can we use a sample to get a good estimate of where the true population proportion is? And that's all we can do. We can only get a range, but it's depending on how big of a sample we can get a pretty good one. So we're going to go through this step by step. As always, our first step is to check our conditions and assumptions. Before we can do anything, we want to make sure we should be doing things. IRS 10% in this case, when we're dealing with proportions, we want to be checking our independence. And given we don't have anything in our information that that speaks to the fact that it's independent samples, but given the fact that they're from 23 states across the country, it's not all that likely that one sample is going to affect another or infect another. So probably safe to assume that the samples are independent. Is it random? Again, nothing specific speaks to that in the problem. We don't know how the sample was taken, which isn't really going to be the case in real life. We would be taking the sample, so we would guarantee that it's random. But again, given what we're doing and given the context of the problem, what we did was go to 23 different states and get 525 chickens from various types of food stores. That's probably representative of the overall population, which is ultimately why we want to do random anyway. That is representative. 10%, 525 is less than 10% of all the broiler chickens sold in the United States. That's an easy, it's not too big of a sample. And success failure, 83% of the sample is more than 10, and 17%, the probability of not getting one with the bacteria is also greater than 10. So the conditions are met. We're going to name our test. We can use a 1 proportion Z interval. That's what we're doing to estimate the population proportion of broiler chickens contaminated with the particular bacteria. Right, so we've checked our conditions. Now we move on to the mechanics. And this is the how we build our sample, or our confidence interval rather. We're going to take our sample proportion, our p hat, right? And that's going to serve as the center of our distribution, because when we knew the population proportion, we put that in the center of our sampling distribution, right? That always wound up being in the middle. Well, now all we have is our sample. So our p hat in this case is our given. This is what we got. Our sample proportion, when we did our sample of 525, 83% were infected. Hope you're not watching this around dinner time. We want to be 95% confident. So 95% confident means we want to have the central 95% of the sampling distribution for samples of this size, 525. So we need the z-scores that correspond to 0.025, right, on either side. And that's 1.966, not 9, and 1.96, both positive and negative. We don't really care. We just want the number because we are adding and subtracting, or better said, the calculator will be adding or subtracting. So there's our p hat. There's our critical value, right? That ties to our that's our inverse norm function from way back in the day, right? and then we take this standard error. It's almost the same as the standard deviation, but it's not the standard deviation because the standard deviation is based on the population proportion, which we don't know. But we have the sample P and the sample Q. So since we're using the sample and not the population, we're going to call it the standard error. But we don't really care. It's the exact same thing, right? So this part that's added or subtracted, the product of the critical value and the margin and the standard error, is called the margin of error, which is an idea that I think most of us have an idea, have at least heard of. Right? And that creates the interval, this right here, 0.798 to 0.862. This is what you show. You show this setup. It isn't the end of the world to do in the calculator. If you have to do it out by hand, you have to just do it twice, one with addition and one with subtraction. That's all. But we can do it in the calculator. We will do it in the calculator. It's just something I want to show you in person, not here in the lecture. So this is what you show to get the interval. That's what we include. And where we get this is really not all that important. Whether we actually do it out or whether we get the spit out from the calculator. So our confidence interval, our 95% confidence interval, is about 80% to 86%. Is where we think the true population proportion is. It's between those two values there. And we always want to include it as a range. It is an interval. That's the very name of it, right? So include both values. Include both values. That's important, right? Now, sometimes as we're speaking to the mechanics, in this particular one, you're given the p hat. You're given the sample proportion. You're not always going to be given, but you're always going to be given enough information to get it. So whether you have to do the simple calculation of the sample proportion or it's given to you, that's all. That's pretty much the only work that we didn't have to do in this particular problem because they gave us the p hat. The z-score, right? The critical value is going to be always going to be the same for the given confidence intervals. 95% confidence interval, the z-score is always going to be 1.96, always, because the z-score is tied to the percentages in the normal curve, right? Not the numbers that got you those z-scores. And for the most part, when we're doing confidence intervals, you're going to be asked to do a 90%, a 95%, or a 99%. And the more you do these, the more you practice these, the more you're just going to commit those things to memory. And there's nothing to show where this came from. And most people just get it from technology. If you want to do, just say something like this, equals, inverse norm 0.25, 0.025 rather, that's fine. Or from tech, that's fine. That's where it came from. But there's not much work to be shown here. Right? And if you are not given a confidence level, go with 95%. Just happy medium, 95%. Right? So we've checked our conditions. We've done enough to do a one proportion z interval, and it's important to name that we're using a z because it's essentially the normal model. We've constructed the interval, and it's really not too bad. But now we want to interpret it. And interpreting it is where it gets tricky. Not tricky, but where you have to be pretty specific. Right? So the first thing we can interpret is the interval itself. The first thing you might be asked to interpret is the interval itself. And what does that interval really mean? It means we are 95% confident that between 80% and 86% of all broiler chickens sold in the U.S. is infected with this bacteria. Right? We're not 100% certain, but we're 95% certain that it's the true population proportion is between 80 and 86. There's a chance that we missed it. There's a chance that this particular sample of 525 broiler chickens didn't actually give us the correct interval. And there's a chance we missed it. But we're 95% confident that between 80 and 86% of all broiler chickens sold in the U.S. is infected with this bacteria. Right? So that's one thing we could interpret is the interval itself, and you should interpret the interval itself. Take the time to make the statement. Include the confidence level, right? Now, they're not going to care if you round it to whole numbers because it's not as though you're going to be any more or less shocked when you say 86 and 80 and 86 or 79.8 and 86.2. It's still kind of a high amount that is of infected chickens, in my opinion. But it's an estimate. It's an interval. It's not a guarantee. So don't get too worried about the rounding. If you want to stick to the actual value, sure. If you want to round, in this case, it's not going to hurt you, right? So you can interpret the interval, and you should interpret the interval with a statement, including the confidence level and the interval and the context. Like, what are we doing? What are we looking? What are we making the interval of? It's the population proportion of infected chickens, right? Broiler chickens, that is. You might also get asked to say, well, what does interpret 95% confidence? What does that mean? All right, well, that means 95% of random samples of 525 will produce the intervals that get the true proportion. Right? If we did this procedure 100 times, right? We went out and got 525 broiler chickens and came up with a sample proportion. It's not always going to be 83%. You could do it again and get a five sample of 525, and the p hat might be 86%, might be 84%, whatever. But we're 95% confident, or 95% of those samples of 525 would contain the true proportion of infected broiler chickens. 5% would miss it, right? Because we're only going out so far, right? This is our sampling distribution, and we've got all the different proportions of 525 that are contaminated, right? But it's only the central 95%, meaning, yeah, there's still a total of 5% on either side altogether, right? That might be outside of our confidence level. Right? So if you're being asked to interpret the interval, always interpret the interval. But you might be asked to, what does 95% confident mean? We're saying 95% of the samples of 525 will actually contain the true population proportion. And that's the difference. Okay? So that's a quick walkthrough on how to construct a confidence interval for a population proportion. In class, we can go over how to use the calculator to give us that interval. But I don't think it's too bad, but practice cannot hurt. So please let me know if you have any questions. I hope this helped.